Hello, welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video we continue talking about linked lists, and we're going to start doing an implementation of a mutable singly linked list. And basically this is what we have in our drawing here that we looked at in the last video, where we have nodes that store some data for us, and they also store a next pointer, and that next will take you to the next thing in the list, on and on until we get something that is null. Okay, so I want to actually write the code that will implement this. And so to do this, let's go ahead and let's create a new class. And how about we call it Mutable SLL for Mutable Singly Linked List. Now, I could make it so that my this Mutable Singly Linked List extended the MyList interface that we created earlier, but I really don't want to do that. I instead would like to have it so that it works with the Scala libraries, because there already is the concept of a mutable sequence of elements built in to the Scala libraries. So we make this so that it takes a type parameter of A, and I'm going to import collection.mutable because I want this to extend buffer. Okay. The buffer type is a sequence type that is mutable, and so now we have an error here because buffer, it turns out, is abstract. Okay, it doesn't have everything implemented inside of it, and so if we go to the API and we go and we look at our buffer, okay, immutable, mutable, there's array buffer, here's buffer itself. Okay. The API actually tells you which methods have been implemented and which ones haven't. And so in this case, it says there's these abstract value members right through here. We have a plus equals colon, the apply to get, a clear, which clears out all the values, insert all, iterator, length, remove, and update. And so I need to put all of those inside of my class. Okay, so we have our code here, and I want to put these methods inside of it. And what I'm actually going to do is copy and paste them in. And I'll have to delete a whole bunch of comments and whatnot in here. In our implementation, they are not going to be abstract. We're actually going to write them. Okay. Actually, it's probably easiest just to delete those lines and say def. 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 I have to admit, this is something that the Java side of Eclipse would have an option for adding all of the unimplemented methods into something for you. The Scala tools haven't gotten quite to that level of sophistication yet. Okay. So, turns out the plus equals and the plus equals colon, whoops, are supposed to return the current object. We have an apply, a clear, okay. So what do we need to put inside of here? Well, I need to represent those things that were in the picture. I have a private var for the head, and when we start off, it's going to be null. Now, the problem with just doing that is then the type is null, and I don't want this to be null type. What type do I want it to be? Well, I want it to be one of those little boxes with 2 elements in it. We referred to that, said we would often use the term node, and indeed we're going to create a type for a node. So I'll create a class node in here. We'll go ahead and we'll make it private. And what does node store inside of it? Well, it stores we'll call it data as an A, and the next, which is a node. Now remember, the way that Scala works with these variables, this is just a reference. This isn't actually a whole node, because then we'd be in trouble. If nodes contained whole nodes inside of them, we'd have an infinite regression there. We're going to need to access these outside of here, and so the question is, should these be vals or vars? Because this is mutable, the way that things are going to work, we can definitely say next is going to need to change, because just we were showing when we were redrawing our arrows in the example in the last video, the next pointers change on a regular basis. But what about the data? Well, this update method right here is supposed to go to an element and change it. And so it turns out the easiest way to do that is going to be to make our data variable as well. We're going to make it a var. In addition to storing the head, I am also going to store a tail. And while this will complicate the code a little bit, I think it's worthwhile to do, mainly because this function right here, the plus equals, is supposed to append to the end of the list, and that gets very inefficient. The other thing I want to add in here actually, if I follow the naming that I did in our last class, I want to declare a variable that has the number of elements. Oops, that's right. I cannot call these head and tail. I always forget that when I write these classes. Because turns out head and tail are defined, well, in buffer, because they're defined way up in sequence. So I'm just going to call them HD and TL so that we don't have a name conflict here. Okay. I like to start with the easy methods. What are the easy ones to write? Well, how about clear, for example? Okay, well, when we clear this out, I'm going to set head equal to null. I'm going to set tail equal to null. And I'm going to set num elms equal to 0. And of course, right now that's what they are, because we don't have the ability to put anything in, but that would send it back to its initial situation. Length. This is another one, another easy one. We're supposed to have this variable num elms, which is keeping track of how many things are in there. Therefore, that is our length. Okay. Running out of the easiest ones, now we get to move up to something that is slightly more challenging with the plus equals and the plus equals colon. Plus equals is an append. It's supposed to add a new element to the end of the list. Plus equals colon is a prepend. It's supposed to add to the beginning of the list. So let's look back at our list, the drawing of it, and when we did this append operation, what we said we needed to do is we needed to make a new pointer. We needed to have the next of the tail point to it, and then we had to move the tail. Okay, so let's try to follow that logic inside of here. I want to make a new pointer, or to make a new node, and I'm going to set tail dot next to be equal to this new node. The data is elem, and the next pointer is null because it doesn't point to anything there. Oops, not tail, TL. I'm inevitably going to do that multiple times. And then TL equals TL dot next. Okay, so this one line here makes the new element and points the tail's next pointer to that, and then we move tail to that next pointer. And theoretically everything's happy. At least for the picture that I had drawn, everything is happy here. But this isn't complete. Okay? And so turns out if we were to run this, the first time we tried to add something, we would get a null pointer exception. Okay? What causes a null pointer exception? Null pointer exception is basically occurs when you have something to the left side of a dot, like this one, and the thing that's on the left side is null. Well, what does the value of TL start off as? That's right, it starts off as null. Okay, so we need to check for a special case. Plus, it turns out when the whole thing is empty, we have the situation where when we add something in, it's not only the tail, it's also the head. So if TL, actually how about I do if is empty, we'll use the is empty that we've already written, or that is part of this. I'm returning a length. I wonder how it does is empty with the built-in. Let's go ahead and let's just say if TL is null. Well, that's my special case situation where I say TL equals new node of elem and null, and then HD equals TL. Okay, so both the head and the tail both point to this one new node. Else, we should do these two lines. And it turns out no matter which sit we do, we have just added something, so num elems plus equals 1. Okay, so that's the append. This method here should be the prepend, where we want to add on to the beginning. So what would that look like in our drawing? Okay, well, I want to add something right back up here at the very beginning. So let's go and let's copy two elements and put them down here. So we're going to make a new node like this, and the first pointer that I have to change is the one that links from here up to here. Okay, if I don't set that pointer, then I have that whole problem where I let go of the rope and my inner tubes float away. Okay. So while I still have this reference to that node, I make something else point to it, and then I can change the pointer down to there so that that becomes my new head pointer. Okay. So what does that look like in code? So by that description, I can actually do this one in one line. Head equals new node elem head. HD, sorry, HD. Okay. So because the right side of this assignment has to happen first, it builds a new node and it links that new node to what is currently the first element. It then, after it has built that, it sets the head to be this new node. Okay, so that all happens in one step. In many ways, that looks just fine. Once again, though, there is a special case. We have this boundary case, and I guess I should also remember to increment num elems. The boundary case here is if TL is null, then we need to set TL equal to HD. Okay, so if we had nothing there, then when we set the head, that new element also happens to be the tail. Simple enough. What you're probably already noticing here is that we have these special case situations that deal with setting the head and the tail, even in the case of prepend and append. Okay, now everything else that we have gets a little bit harder, kind of a step up in difficulty. We'll write maybe two more in this video, and then we'll come and complete the others in a subsequent video. Probably the next easiest one to write is apply. Okay, so how do we write the apply method? Now note, I'm writing these things, but we haven't tested anything. We really should wind up writing unit tests and make sure that these things do what they're supposed to do. So when I call apply, what that's supposed to do is it's supposed to go through the list. So if I call apply and I pass it 3, well, this is the value at element 0, 1, 2, 3. And it should give me back the value that is stored in this node. Okay, this act of going through, we refer to this as walking the list. And so I need to walk the list to get to the correct element. Okay. So what I'm going to do is I'm going to create a var. I like to call my var for this purpose Rover. You could call it a walker or runner or whatever you wanted. It really doesn't matter what you call it. What matters though is in the long run you should probably be consistent. That way when you see this variable name, when other people have been reading your code and they see this variable name, they know what it's doing. I always use the variable name Rover for something that walks through a linked structure, okay, like this linked list. If I use you'll never see me use the variable Rover for anything else in my programs. And so it's automatically clear what a Rover variable is doing for me. Okay, and so whatever you call it, it's good if you can be consistent with that. Now, we need to have this Rover, and I'm also going to make a var. Let's do this. I can do this nicely with a for loop. For I in 0 until n. Note that if n is 0, this doesn't happen at all. 0 until 0 doesn't go anywhere. And what I want to do in here, actually, I can compress this down to one line. I really don't need Rover equals Rover.next. So we start Rover at the head, and then every time that we go through this for loop, we move Rover to the next value, and when we're done, we return Rover's data. The end. Okay, so that's all that was required for our apply method. There is something that we should consider doing in here, though. What happens if they ask for an index that's out of bounds? Well, depends on what index they ask for. It turns out if they ask for -5, given this code, we're going to return the first value to them. And maybe that's not what we want. We really should be throwing an exception or something along those lines. If they ask for something that is too far, we'll throw a null pointer exception. And the reason for that is because if my list has 5 elements and they ask for number 10, we're going to hit a certain point where Rover goes to null because it's moved past the end of the list, and the next time through we're going to ask for null.next, and that'll throw a null pointer exception. The null pointer exception is closer to what we want than just returning the first element and acting like everything was happy. However, neither one of these is really ideal. Because we want to throw an exception that is informative. Okay. Requested in of num elements, and we want to do this in the situation where either n is less than 0 or n is greater than or equal to num elements. So if they ask for something that's out of bounds, we want to throw an exception, and we'd like for it to be an informative exception. So it as opposed to just automatically throwing a null pointer exception, and then the programmer on the other side wonders, why the heck is this a null pointer exception? I don't have any null pointers anywhere. It's because buried down in your library code, you made something that produces a null pointer exception when they go out of bounds. But we want to make it easy for them to see what's going on. That's one of the real advantages of exceptions. Okay, so that's the apply method that looks something up. The opposite of apply is update. And so how about we do the update method. Turns out the update method looks a whole lot like apply. And in fact, you'll kind of see there is a theme here. A lot of these methods wind up looking similar because they have this rover that has to walk through the list. So once again, if they ask for something out of bounds, we're going to throw an index out of bounds exception, tell them that they were updating the wrong value. We start Rover at the beginning. We walk through in the same way, and the only difference here is what we do once we get to it. We do not just return the value, we overwrite it. And that's why I made the data mutable, because for update, that is the easiest thing to do. So we still have a remove method, an iterator method, and an insert all method that we need to implement. But once we have those, we'll have a complete implementation that we could test, and we'll come back and we will work on those in the next video.